Great. Okay, so let's talk about imperfect information. So so far we talk about again game theory motivations, normal form game, and several concepts of like essentially. So we are talking about two important things in this class, two threads. One is a different form of representation of a game. The other one, what are the kind of settlement or equilibrium concepts that we are talking, or solution concepts. Here we will go more about, and these are somehow correlated. So for example, we talk about Nash equilibrium or Pareto optimal thing. These are more like we define for normal form games. Then we talk about the sub game perfect equilibrium, uh, SP that we are talking about, this kind of perfect information games. And here, so there are also these solution concepts and the way that we are representing these games, they are related. Here we are talking about, but one thing we have seen it. We have seen that the normal form games are somehow more general than perfect information game, because any perfect information game, you can actually make it a normal form game. We haven't seen quite equivalence there. And one issue is that, yes, we have some kind of temporal thing in information, perfect information games that say, you will do that, then I will do that, then the other person is doing that. This is a bit different from normal form games that we are doing simultaneous. So the idea is that can we maybe make it a little bit more general, perfect information game, to make it imperfect information games actually, such that we can say now that we are at the equivalence system. And that's the idea of imperfect information games. And then there are some kinds of equilibrium that come with that, and it's quite actually interesting. Good. So with this introduction, let's go through this one. So at in the extensive form game, so far we have assumed that a node know all prior choices that he or others have made. And that's the thing that we call it perfect information. Again, both their moves and the other people. But sometimes it might be the case that you don't know the actions, all like actions of others. They are like more private things. You know that you reach to this state, but you don't know what all other people have done it. Especially if the number of players are more. Sometimes even you don't recall your past actions. You may have done something in the past and you have not written. You don't know. And this is like search tree we are talking about, or game tree, and we are quite deep there. You don't know what you have done it before. So here we try to essentially consider some concept that can essentially address this kind of ignorance. And we have some kind of, sequencing. That sequencing can be very useful for some cases. But the issue is that it cannot handle all cases. And in particular, the concept of simultaneous move is one of the things that was essentially missing in current extensive, perfect information extensive form games. And that's the thing that we try to address it. Good. So this is the things. So in the imperfect information game, agent choices, or actually even the agent's choice nodes, are partitioned into informations. And what's the meaning of an information set? So information set is the all choice nodes, like in the tree that we had it there. So we may say that, for example, just change the color. So for example, we can say this, and this all are in the same information set. And this is essentially means all choice nodes that an agent might be there. And this is the whole idea that we have this tree. In addition, we have these information sets. And the idea is that when an agent is here or here or here, that agent does not know. Knows that in one of these nodes, but does not know essentially in which one. And thus, it does not know how did he or she arrive at this. As I mentioned, the nodes in the information sets are indistinguishable to the agent. And as a result, that one other thing is that they should all have the same, essentially, set of actions. So if you consider this one, so the set of actions that they should have, for example, all essentially R and L, R and L, R and L. So it cannot be the case one is, for example, R and C. No, there is nothing like this. It should be R and L. Because if you are at the same node, you have the same information. The set of actions that you have should be the same. So that comes naturally as part of the definition that the nodes in the information set are indistinguishable. It means that the set of actions should be also the same. Because otherwise, you are in which. So that's the idea. So a perfect information game is a special case of this kind of imperfect information game that essentially each of these guys have a different color, or each of these nodes are its own information set. So no two nodes have the same information, are in the same information set. All of them have a unique and distinct information set. And again, what are the properties of this information set? They should have these properties. They should form a partitions of, this essentially says partition nodes in the tree. They should partition. What's the meaning of partition? It means that all nodes so if you take the union of all of these, should be the all nodes. And any two of them should have essentially zero intersection, because you cannot be at two information sets at the same time. It means that this information set should be the same. And as I mentioned, all available actions for any two nodes which are in the same information set, all available actions are the same. So let's see an example. Good. So here, consider this game. Agent 1 has two informations. One is this one, that agent 1 has just in the node W. We have a unique name for each of them. And agent 2 is in this node Y and Z. These two are in the same set, and we are just representing them by putting this kind of dotted line or dash lines. It means that they are in the same information. So what's the meaning of that? It means that if the agent in the information set I12, then agent 1 doesn't know whether agent 2 was C or D. It may have some information. It knows that, for example, is coming from A, but it doesn't know what was the agent 2. Was it took C or D? Because they are the same informations. Here, agent 2 has only one information set, and this is this one. This is for agent 2. Yes. Good. Now, so this is one example of them. And again, this kind of dotted line or dashed lines is the one that is important to show that these two are in the same information set. It means that, and note that here the actions that they have it here are the same. So, I mean, actually the payoff might be different because that's the thing that they will see it after that, but action set should be the same. Or after that, it might be different, but anything essentially, this one up to this here. So other than that, the actions, the other nodes below or others, so they may later understand, but that is gone essentially when they know that. So what about the strategies? So we need to define the pure strategies. So a pure strategy for agent I is essentially function Si. So that selects for any that essentially for each information set, you should say which action you will take. So this is just a generalization of perfect information game. Why? Because if you remember, I mean, what did we had it? We said that like if agent 1 appears here and here in the perfect information game, so that okay, you need to essentially a pure strategy that here you need to say, for example, you will take R and L, and here you need to say whether you will take C and D. So you need to say that, and all possibilities would be all pure actions. Here, we just generalize it because essentially more nodes can be in the same information sets. So that means that you need to say for each information set, which action should I take? And as I mentioned, all the nodes in the information set have the same set of actions. So if you take one action, that action applies to all of them. And the set of all pure strategies for agent I is just a Cartesian product of this. Essentially, this kind of tuples that say that for the first information set, which action you will take, for the second, what do you take, third, fourth, and so on. So let's see an example here. So for agent one's pure strategy here, so agent one has A, B here, and then here he or she has EF and EF. So here, so if it was if these two nodes were, if this dotted line was not there, then you need to say, for example, A here, E here, and I don't know, F here. But here we don't have this one. We only say A, B here, and then E or F. And E or F would be the same in both of these cases. So here, so that's the one that we have. So here we have AB times EF. And this is the Cartesian product, means essentially all the pairs that the first one comes from the first one, second comes from the second. And here the agent 2 pure strategy, that is like this before. Agent 2 only appears here, so we can take C or D. So it has these are the pure strategies.
I have a question.
Sure.
So when if agent one takes action B, then there's no action where agent one can take E or F. So aren't the two two elements on the right side of the set like kind of invalid, like BE and BF?
Yes, I mean these are all. I mean that as I think we had the same issue. This is not just unique to imperfect information game. This was also correct for the perfect information game.
Yeah.
Yes, in that case, I mean when you take B, then E and F in some sense are irrelevant. You can think about it that way.
Okay.
So
And then,
you have BF, you have BE, but they are the second one is irrelevant because you already know what is that. So we can say, okay, there was this one, BF or B, both of them you get 1, 1. So that's the utility.
okay, thank you.
Sure. Good. Now, so this is always the case. So we want to, what was the idea again? The idea is that, okay, we want to see what are the pure strategies and then mix a strategy and how can I represent this a bit more general set of things? As I mentioned, this generalizes the perfect information game because in the perfect information game, each node is it's on its own information set. So this is just generalization of that. We want to see that can we still represent this one in the normal form games or not? So the idea is essentially the same thing that we have done it for perfect information game. Now that we have defined pure strategies here, then you can form actually the normal form games. And it is exactly the same thing as before. So for example, here, to form the normal form case, you need to say what are the pure strategies for agent 1 and agent 2. So this is agent 1. This is agent 2. Now, this is the thing we talk about the pure strategies already. Now, how can we get essentially the utilities for each of them? So again, what do we do for agent 1? To do that, so for agent 1 here, we say AE. So here we said, okay, you need to just essentially consider this edge A. Then E you should essentially color not only on Y, but also on all information sets. Now, what about for agent 2 here? So for agent 2 here, for example, we do C. So that's C. Always, there is a unique path. If you do that, if you have done correctly with your uh, pure strategies, uh, and you have written the correct Cartesian product, always there is a unique path from the root to one node. Because by definition, essentially, because in all of this, you have decided which one. And again, the information set, you will say which action, but again, this action will apply to all of them. So there is one unique path that goes to one utility function. This is, again, by definition, essentially. That decides the payoff here. So if, for example, if it's just doing this, so if this action, instead of this action, agent 2 is, instead of C, is doing D, then it would be like this. That would be the unique path then. And then you get 2. So this one, essentially, you can do that. So you can get the normal form gain. So all concepts are coming. Nash equilibria, Pareto optimal strategy profile, etc. All of those that you can define. Some of this, like subgame perfect equilibria, I mean, this is not, I mean, you can still define if the information set has line, but some of them may change essentially. We may not have all the properties as before. This is, we mentioned for 2 agents, but you can represent this one for any n-dimensional thing. So like with n players, you can have essentially n-dimensional matrix normal form game and represent. So this is somehow, everything can be done still in normal form game. Very powerful thing. Now we had one goal in your mind. What was the goal? The goal was this one. What was from normal form game to extensive form? We talk about it, yeah, perfect information game. We could also do that in normal form games. But it is interesting. When you have different modelings, uh, like you may have different modeling for a problem. But like for example, if you are working on the complexity classes like polynomial, MP hard or MP complete, there are lots of other complexity classes in the algorithm design. There also you have different classes or different models essentially. An interesting thing happens if you say that two of these models are equivalent. That means essentially some kind of deep dive. Say, oh, I have considered this and this. They are the same. The same thing happens for LP. You may write essentially some linear program for a problem and another linear program for the problem. And because there is no unique way of writing it, you may have write it actually differently. Interesting thing happen when you say that these two linear programs are equivalent. They give the same solutions. So anytime two things happen at the same time, generally, I mean, it means that something non-trivial happened, and these interesting things happen. So the people always think about it in general. Like if you have one solution, the other person has another solution. It turns out these two solutions are the same. Generally means that, oh, you were essentially this kind of sanity check. Two different people reach this one. That seems probably a good solution. But the same thing here. How can I essentially turn, can we, so far we couldn't model normal form games in terms of perfect information. What about imperfect information games, or essentially imperfect extensive form games? A normal form game can be transformed into an equivalent extensive form imperfect information. To do so, if you have n players here, yeah. So if you have n players here, then you need to have n level game tree. And what we do is this n-level game tree that you have, each agent has exactly one information set in all these levels. Like agent one would be the first level. There is no difference. Agent one can be the level 0 or like the top guy. And the next one can be agent 2 or vice versa, as you will see it. Each agent take essentially one layer, and all of these nodes. So essentially, this is like the thing. So this is agent 1, for example, is here. Then agent, I don't know, here, for example, agent I. In this agent I, all of these guys in this level will be in the same information. So all are in the same information set. Good. And that's it essentially. So we will see an example. But here, when we do that, essentially then we say that we have the same strategy, same payoff. And so the Nash equilibrium, Pareto optimal strategies, others, correlated equilibrium, all of them you can define it. Let's see an example. So this is essentially the prisoner's dilemma things that we had it. So here, this was the normal form game that we had. Good. So I will say that consider the agent 1 here. Agent 1, what are the actions that he or she has? Has C and D. So this is C and D. What about agent 2? Agent 2 is here. It has agent 2, he or she again has C or D here. Because like this is agent 1 and this is agent 2. So here, agent 1 is here, agent 1 is here, agent 2 is here. And they have the same information set here for agent 2. So agent 1 is doing C and D. It is its own information set. There's only the information set has size 1. But here for agent 2, there are 2 nodes here, C and like this one and this one. Both of them have the same action set. What are the action set? These are C and D that it has it here. So what's the meaning of that? This is exactly the meaning of simultaneous game. It means that when agent 2 is doing the move here, does not know which action agent 1 is taken. It was C or D. You don't know which one. You take the action, and then you will reach to your essentially payoffs. And here, so yeah, if you do DC, for example, here DC would be 0, 5. Like I think here is D here and C here would be 5, 0. And so on. Equivalently, you could do it like this. Agent 2 can be the root node. And agent 1 is the one that comes in the second. No difference. So this concept of information says actually that, you see, that's the beauty of that. This is, maybe I will say, oh, it is just some definition. But somehow this definition is put there in a wise manner, such that you will see, oh, this information set is some kind of minimal things that I can add it to perfect information set, such that I can get the equivalence. In general, when you try to do modeling of the game or solution, you don't want to make it complicated. You always want to go with the simplicity. So simplification is like it means great, essentially a better understanding about it. Of course, you should try to consider constraints, but at the same time, you should try to give the simplest solutions, at least at the beginning, or simplest model. Later, when you have the simplest model or simplest solution is the one that you can build on it. It can be a baseline. Say, okay, I have some baseline. I know that it works. It is correct. Maybe it's not the best solution. No, you can make it more complicated, more efficient. That is totally fine. But not at the beginning. That's the thing. Just adding this concept of information set that 2 nodes have the same information set. They are indistinguishable, essentially, when you are there. Then you can actually model normal form game now. Now, say if we have n player, each of them have 2 actions. How many nodes do we have in this graph? So I have n players, 2 actions each. What will be the size of the normal form game in this case? Yeah.
So normal form game will be 2 to the n.
Yeah.
The tree will be 2 to the n minus 1.
2 to the n minus
1 on the outside. So 2 to the n. Okay.
Yes. Good. So if you have essentially, like in this case, n player and 2 actions each, normal form game, we already knew about it because this is. So for the first one, you need to see how many pure strategies we have. It is 2 times 2 times 2 times 2. This is very important. And that would be 2 to the n. So that was the size of the normal form. It is maybe times n as well for the utilities. But what about this game tree, essentially? Then you can say the depth of this would be n. All these guys would be the nodes, the last level would be 2 to the n levels. That they are representing the information set. Okay. And then you can say in this game, actually, the number of internal nodes. So the external node would be, external node. These are outside one would be 2 to the n. What about internal nodes? That would be the number of external node minus 1, essentially, in this case, which would be 2 to the n minus 1. So essentially would be 2 to the n plus 1, which is the same, essentially, up to a constant, it's just constant. Yeah. So this is important because when we went from some of this perfect information game to imperfect information game, actually the size of the normal form matrix was very small, but when we like the size of the tree was small, but when we have done a normal form game, actually we could have a very large normal form matrix. And as we discussed, like one payoff, essentially it may appear several times in the thing. If you remember, we had some game, and then say, for example, 3-5 appears here, 3-5 appear here, and 3-5 appears here. In particular, I mean, we may have exponential blow up when you go from a tree size space versus a normal form game. The size can be actually quite large. But here, not much blow up. So that's a good model, actually. Good.
Can you quickly go over the oh sorry. Can you
You
go
go ahead.
can you go over the 2 to the n plus 1 again? Because
Yeah.
if let's say for Prisoner's Dilemma, um you have two players, right? So you do 2 to the n plus 1. If you plug
Yeah.
in two, you get like 8, but there's 7 nodes here.
Okay. So here, so what was that? So here we have 2 to the n here. N is equal to, so it is, in this case, we had, again, n players, 2 actions each. So here would be 4, essentially, 2 to the 2, which is 4, correct? So we have 4 people here, 2 to the 2 here. And then the number of internal nodes would be 2 to the, oh, sorry, that was actually, maybe say thanks for that. So it would be 2 to the 2 minus 1, not 2 to the n minus 1. 2 to the, so here we had 2 to the 2, which is 4 here. And here 2 to the 2 minus 1, which is 4 minus 1, which is equal to 3. And the total nodes would be essentially 2 to the n plus 1 minus 1.
Okay.
In this case would be essentially, you will put it 8 minus 1, which would be 7.
Okay, thank you.
So, good. So that's the thing that we are we discussed, and thanks for asking the question. So let me clear everything. Good. So we have seen essentially the essentially imperfect information game. We can model normal form game and vice versa. These are the same modelings. Now let us talk a little bit new class of strategies. So far we talk about pure strategies and like essentially mixed strategies, and we have mentioned how you can get it. But for these games, for imperfect information games, actually, you may. So here we know that this, for example, this is the example. This agent two, these two are the same information set. The issue is that you don't know how do you reach there. So did you the agent one take A or agent one take B? That was the idea that we had the randomization in the normal form game. That you are, I mean, you don't know the actions of the other guy. So in the normal form game, and then I may do the mixed strategy. Mixed strategy means random. So here, uh, you may define essentially the case that each agent, it can take some kind of probabilistic actions. The same thing that we had it there. So we are in the imperfect information game. So I decide that the actions that I have it, with which probability should I take? So because I don't know the whole history anymore, it is because there are some simultaneous moves. Now I can model it on it. Now let me do some randomness at least, or mixed strategy. So for example, consider this imperfect information game here. So for this is called behavioral strategies. So a behavioral strategy for agent one would be like this. For agent one, you will say that I will put it 0.5, like with probability half, I will take A, with probability half, I will take B. Now at node G, I will do it with probability 0.3 G and with probability 0.7 H. So here, essentially, I will pay 0.5 here and 0.5 here. And here I have 0.3 and 0.7. And here we are assuming that at each node, this essentially, the choice would be independent from the other choices. So there is no correlation, because that can make the things hard. So here, yeah, so you can get it 0.5, 0.5, and 0.3, 0.7. Now, this is somewhat similar to mixed strategies. Are they equivalent or not? Of course, then we need to define what's the meaning of equivalent. Good. So we need to define the concept of equivalent. We will say two strategies, Si and Si prime, for agent I, are equivalent if for every fixed strategy profile, S minus I of the remaining agents, Si and Si prime give us the same probability outcome. So these two strategies that I have it here. So this strategy, you may get it. So this is the strategy. You will say for agent one, what is the probability here that you will do it 0.5, 0.5 here, and then here you have 0.3 and 0.7 here. So these are the probabilities that you have. And then, of course, then what is the probability that you will end up here, for example? What about the probability that is here? To say that this, so can I make another mixed strategy? Note that the mixed strategies will be defined on the pure strategies, on the set of pure strategies. So that's the same definition that we had it there. So you need to find all pure strategies, and then I will say randomize over those pure strategies. Having said that, this behavioral strategy that I have done it here and this mixed strategy that I have done it here, are they equivalent? What's the concept of equivalent? Means that if these two are equivalent, any other actions that other people will taking, the result that I will get it with this strategy versus this strategy, they should be the same. So, for example, here, you can see that in this case, an equivalent mixed strategy would be this. So AG, so I need to say what are the set of pure strategies. I need to say all pure strategies that I have. It was AG, so this is AG, AH, BG, and BH. So AG is 0.15, AH is 0.35, BG is 0.15, and then BH 0.35. And I just multiply this one. So this is essentially this one. So what is the chance that you will get it here? It would be 0.5 times 0.3. Here it would be 0.5 times 0.3. In this case, they are equivalent. You can show that any strategy that others are doing that, if I do it here, this would be the same. At least in terms of mixed strategies. If you consider all the mixed strategies of others, if I do this behavioral strategy versus this mixed strategy, I will get the same result. But of course, in this case, they were the same. But are they always the same? Or one is more general than the other? Mixed strategies versus behavioral strategies. Let's see that. The main idea is a correlation. So do I add any correlation during this or not? That's the whole idea. We will talk more about it. Good. So these are consider the following mixed strategy. So we want to understand again. So this is the same thing. We had some model, imperfect information game. So the normal form game is the same. What about we had pure strategies? We can define it. Mixed strategies, we can define it. But in this game, actually, behavioral strategies make sense because at each node you decide which probability you want to take any of these actions. Is it the same as others or not? And as I mentioned, always this happens. It means that some non-trivial things happen generally. So consider this mixed strategy. So in the mixed strategy, I will say AG. So AG, I will take it with 0.6, with chance 0.6. And BH, I will take it with probability 0.4. Good. All other cases, in particular, for example, I have AH as well as BG. Both of them would be, essentially the probability would be 0 for this case. So here, you will see that the choices at the two nodes aren't essentially independent. So here, agent 1, if it takes A, then it takes G here. And if it's taking B, action B here, then it takes H here. This is correlation. In a mixed strategy, you can define this essentially over this set of pure strategies. However, this is you cannot essentially, because of this correlation, because if you do AG, then you do, if you take A, then it is G. If you take B, then it would be H. So in this case, I mean, fortunately or unfortunately, I don't know, this is just some model. There is no equivalence. And that was the whole idea. What was the whole idea of this kind of behavioral strategy? That you will put something here, I don't know, 0.5 here, 0.5 here, and then you will put 0.3 here, 0.7 here. So the choice here would be independent of the choice here. Because it is 0.3, then you will put again 0.5 here and 0.3 here. It will be just multiplied. But here, essentially, we have made these things correlated. Like the choices here and the choices here are correlated. And this correlation, actually, we cannot make it by behavioral strategies because these are done independently. So there are some mixed strategies that behave, there are no equivalent behavioral strategies. Good. Now, okay, so that's it. Maybe we have these behavioral strategies and then we cannot handle it using mixed strategies, seems more general. What about vice versa? Can we say also the case that maybe behavioral strategies can do that mixed strategies cannot do that? Let's see. So that's the interesting thing that is. So there are some games in which the mixed strategies, that they have no equivalent behavioral strategies, as we discussed before. But there are some behavioral strategies that there are no equivalent mixed strategies even for. And mixed strategies were quite essentially interesting. So essentially means that the mixed and behavioral strategies can produce different set of equilibria, if you want to consider it. And these are both interesting and natural, essentially. One comes from normal form game, the other one comes from the fact that we are representing it essentially as a tree or a graph, essentially. And this is more generally, if you consider, you can consider it as a graph, essentially, that would be Markov decision processes that are essentially like this. Let's see this part. This part still we need to show. Behavioral strategies for which there is no mixed strategy. Consider the game below. What is the game here? This is agent one. This is agent one. So here, and then this is agent one, agent two, and then this is the case that we have it, that agent one and agent two, like agent one is taking some action, and again, it comes in the same information set. So here at both A and B, agent one's information set is the same. They are in the same information set, so the actions will be the same. So here you had L and R, here we have L and. The question of can this happen? Potentially, you can think about this one, that maybe the agent one is doing that and then just forget about it. Maybe after some time is doing that. It can happen. So let's see what will happen in this case. So here for agent one, okay, so for agent one, we need to say what are the pure strategies. So pure strategy, agent one appear here and here, only one information set. So for pure strategies, it has L or R. These are the only pure strategies for agent one. So any mixed strategy for agent one is say that take P with probability L and like essentially L with probability P and R with probability 1 minus P. So here, agent one either choose L or R, but the catch is that if you take one of the actions because of this information set, you should commit to this action. You can do randomize, but you need to commit. So if you choose L here, then you need to choose L here. Then you will end up here. If you choose R, I mean, like as an agent one, then you may, so this is agent one, then depending on agent two, you may end up here or end up here. The issue is that you never can come to this. So this is not possible that you can come to it. Now let's consider the behavioral strategies. What will happen in the case of behavioral strategies? So in the behavioral strategies, I have essentially Q here and 1 minus Q here. So the same thing here, essentially. It would be Q here and 1 minus Q. Because these are the same information set. You should have the same. Now, and this is essentially the one that I have it. Now, what is the chance that essentially we end up at E? Here it would be Q if you take this one, and then 1 minus Q. So that would be the probability that you will end up at E. So the probability that you will end up at E would be greater than 0, except when Q is equal to 0 or Q equal to. If you define Q not equal to 0 or 1, so if P and Q, both of them are equal to 0, then you can say that actually we are always going to L, and this would be equivalent. If P and Q, both of them are 1, then both strategies are ending at purest. That would be essentially purest strategy R. So unless essentially like P and Q, if P and Q are 0, both of them, or 1, these two will be equivalent, these actions that you have.
I have a question again. If P and Q are equal to 0, wouldn't the pure strategy be R instead of L?
We are going back essentially. Let me share a screen. Good. So recording. Yeah, I think. Yeah, thanks for the question. Yeah, this was actually correct. So this, if what did happen? Yes. So thanks for the question. So here we had this one that if P and Q equal to 1 here, then actually is we get a pure strategy L, and if it is 0, then we get pure strategy. So that's the case. So we have, yeah.
Can you fix the slides on the website so that when we're reading the slides, we don't.
Yeah, we try to do it. Good. So this is the one that we have it. And this is the interesting thing. So the behavioral mixed strategies are essentially not necessarily equivalent. One question as a problem or question as an exercise that you can think about it. What about if we don't have this kind of a node? We don't have this kind of information set that from a node, like essentially from a node goes to its descendants. So here from A, we have B, we have this kind of dotted lines that goes from a node A to its child. In general, you may have from A to go something like this to D. What about if we don't have this kind of dotted line? Can we say in this case that these behavioral strategies are a special case of mixed strategies or not? This is a good exercise you can think about. So that is exactly the way that we always essentially handle this problem. So we try to do the modeling. So these are sometimes equivalent. That is very good. And then the interesting thing that, okay, mixed strategies is natural set for this type of representation. Mixed strategies for that, are they equivalent? No, they are not equivalent. But under which condition they will be equivalent? That would be nice because you essentially you are doing a deep dive and try to understand these games better, and you can do more reasoning about them. And these are, again, both of them are a very natural set of strategies, and you can think about. And again, you can think about it, you can search on the web and do that, but that would be a good exercise. I think first think about it, see whether. Good. So I think I stop here.